Welcome to Lab 2. As you can see in this overview, we are currently in Lab 2. We've got 2 more labs to go before Assignment 1 Part B is due. In this lab, we'll be going through displaying the numbers on your 7-segment displays, and we will take you through the design process to draw your schematics for your multiplexers and decoders, and that will lead to the control architecture, which will give you an idea of what's needed to switch on to display a number on your SSD. And we'll finish it up with the tasks you're required to finish for Lab 2. On your MXK, you have 6 7-segment displays. So in each one of those segments, you have your segments A to segments G, as well as your decimal point segment. Light emitting diodes, or LEDs, are semiconductor light sources. They emit light when sufficient voltage is applied on the anode terminal. Now, this emission of light is caused by the LED becoming forward biased. Now, the sufficient voltage is also known as your threshold voltage, as you remember from your lecture videos. Now, due to the semiconductor nature of the LEDs, the brightness of them are directly proportional to the current being passed through it. For each of your 7-segment displays, the LEDs are connected in parallel to a common anode, as shown in this image. Now you can see that for each of these 7-segment displays, all these LEDs corresponding to each segment is connected to this common anode. Now for all of these 7-segment displays, there is a set of common cathodes which are connected in parallel. These cathodes are your outputs from your hex to SSD to determine whether the current passes through each LED for each segment. So for example, segment A is actually one wire that connects to all the segment A's of your 7-segment displays. Now, at any point in the MXK's operation, only one of the 7-segment displays can be powered on at a time. Now, since we have 6 of them, or in order to display multiple 7-segment displays, you need a refresh scheme. So for n amount of 7 segments to display, you need each one to be powered in sequence. The sequence has to be quicker than the critical flicker period of the human eye, to give the illusion that all the 7-segment displays are switched on at the same time. Now this is similar to how if you look at videos on specifically slow motion videos of cars or lights, you can see that the LEDs at a slow enough of a frame rate, you can see that the LEDs are actually switching on and off constantly. And because it's quicker than the critical flicker period for the human eye, we look at these, say, headlights to be switched on at all times. Now, for the refresh sequence, say we want to display the number 1830 on 4 of our SSDs. The refresh sequence would go as such, where at t is equals to 0, the first digit is displayed. At t is equals to 1, the second digit gets displayed. And t is equals to 2 is the third, fourth, and then it repeats. So notice that at any one time frame, only one of the 7-segment displays can be switched on. Now this cycle repeats continuously to give the illusion that all 4 of them are lit up at the same time. Now, in order, as each of the 7-segment displays are powered on in sequence, the data set that you push into hex to SSD will need to change to reflect the corresponding data. So for example, at t is equals to 0, the data set needs to be corresponding to 1. At t is equals to 1, the data set needs to correspond to 8. Now a multiplexer selects the data source to output based on the select lines. So if you look at the image on your right, based on you're up to n select lines, you you would output the data set corresponding with the select lines. So for n select lines, you can have up to 2 to the power of n data sources. Now, notice that we say that there can only exist at most 2 to the power of n data sources, which means that less than 2 to the power of n is possible. So multiplexers such as 6-to-1 multiplexers with 3 select lines are possible. You could also have multiplexers as a 6-to-1 multiplexer with 4 select lines. And from the previous example, we're trying to display 1830. There are 4 sets of data sources to choose from, meaning you'd require 2 or more select lines. Now, let's look at the example of a multiplexer, 4-to-1 multiplexer. Now, based on the truth table, as we can see below, based on the select lines, so select 1 is the higher bit and select low is the least significant bit. Based on the select lines, the output would then be the corresponding sets of inputs. So at 0, 0, your output is input set 0, and at 1, 0, your output set is 1, 2, and so forth. Now in Xilinx, your 4-to-1 multiplexer symbol would look something along the lines like this. So you draw out your schematics, you check your schematic, and then you create your symbols, and the symbols should come out along the lines like this. And from this truth table, you should also derive the Boolean expression, and this Boolean expression is what forms your schematics. So for example, in our example, you have output is equals to S1 bar, S0 bar, I naught, and that would be a AND 3 gate with B2, so AND 3 B2, meaning it's an AND 3 gate with 2 inverters at the front, and then for all 4 of them are then linked to an OR 4 gate, so it's OR 4 gate, and your output is then based on that. Now, the previous example was just a 4-to-1 multiplexer, which means given 4 data sets, you can output 1 data. Now, for 4 outputs corresponding to the 4 bits, you will need 4 multiplexers, or 4-to-1, thus the naming quad 4-to-1 multiplexer. So given the 4 outputs that you need, W, X, Y, Z, remember that W, X, Y, Z needs to feed into your Hex2 SSD, which you completed last in Lab 1. In order to get the 4 outputs W, X, Y, Z, you will need to multiplex which sets of the W, X, Y, Z to display. And that truth table is shown now. So given your select lines, you would then output specific bits. Now, in Xilinx, you are allowed to group multiple lower level logic blocks together to form higher level logic blocks. So in this example, your quad 4-to-1 multiplexer is actually just made up of 4 4-to-1 multiplexers. When you create the 4-to-1 multiplexer, you create that symbol, which can then be reused in your new schematic, which is called quad 4-to-1 multiplexer. As you can see, there is a 4-to-1 multiplexer corresponding to each bit of data, so 1 for W, 1 for X, 1 for Y, 1 for Z, and then these are all shared, they all share the common select lines, as it should be. So based on the select lines, the W, X, Y, Z outputs should correspond. Now, when we talked multiplexing, that was to do with the data sets that we feed into the 7-segment displays. Now we need to look at the sequencing to power on the SSDs. In order to sequence that power on, we need a decoder. A decoder expands select lines into possible outputs. So if you look at the image on the right, you can see that given n select lines, you can have up to 2 to the power of n outputs. Now let's look at an example of a 2-to-4 decoder given this truth table. So you have your 2 select lines. For each case, they correspond to an output So for 0, 0, only D0 would be switched on, but D1, D2, and D3 would be switched off. And as you can see here, the Xilinx symbol that you would create would look something along the lines like this. Given your 2 select lines, you have 4 outputs, and each one of these outputs would have their own Boolean expression. So for D0, the output is only 1 when I1 and I0 are both 0. Now, looking ahead at the bigger picture, this is the 7-segment display control architecture. Now, if you look up over here, we have the quad 4:1 multiplexer that we looked at just then. We have our 2:4 decoder, the hex to SSD, which was completed last lab, and then we also have a sequencer. So, as you can see in this example, your quad 4:1 multiplexer, you are multiplexing through the 4 sets of data that you need, so 1, 8, 3, 0, and they correspond with 1s and 0s, obviously. And as you can see, for number 8, W is 1, the X, Y, and Z are 0s, as indicated with the ground and voltage source. And notice that the sets of data gets fed into your hex to SSD in order to show which data. Now your 2:4 decoder then determines which of your 7-segment displays are then powered on. And the sequencer down at the bottom left is currently out of the scope of Lab2, as it is a sequential logic circuit as compared to the quad 4:1 multiplexer, the hex to SSD, and 2:4 decoders, which are combinational logic circuits. But the basic gist of the sequencer is that it expands the clock input into your select lines. A sequencer can be however many bits you make it to be, so it could be 3-bit, 2-bit, 4-bit, 5-bit. Now, if you remember back earlier on, we talked about a refresh sequence or refresh architecture that would be needed to power on your 7-segment displays. Now, given these 4 components, this would be the output. So as you can see on your right, you have your 4 7-segment displays with their own common anodes, as well as the common cathodes, which are your 7 segments itself. So the sequencer at t is equals to 0 will give out a select sequence of 0 and 0. Now that this select data is fed into your 2:4 decoder as well as your quad 4:1 multiplexer. So as you can see, your first set of data 1 is then chosen to be displayed, and in your decoder you can see that D0 is switched on, which means the first 7-segment display is powered on. Now as you go through the sequence, you can see that now the second segment 7-segment display has been displayed, and it's the second set of data that gets displayed, and this continues as similar as we talked about before, and they continue to refresh until it becomes a 4. It shows up as 1830 on your 7-segment displays. Now for Lab2 tasks, you are to extend the 4:1 multiplexer to fit your assignment. So remember that in our example, we're only displaying 4 of the 7-segment displays, whilst you have 6 digits in your MXK that you need to display. And you also need to extend that 2:4 decoder to fit your assignment. So we had 4 7-segment displays to power on to sequence through the power. Now we have 6, and remember that with n select lines you can have up to 2 to the power of n outputs. Now for references for this lab, mainly it would be the lecture videos on UTS Online, so do look through them if you still struggle with the content.